Thanks for inviting me. So this is a talk I gave just once to a machine learning audience, and my mental model of how the alignment between machine learning audience and you might be wrong. So in any case, this is really a call. Interrupt me at any time. I don't want to rush through the slides, so I'm happy to step back and discuss more in detail if there's something you didn't understand. If you're asking yourself a question, it's likely that someone else is asking themselves the same question in the room. So please do it. This is actually the talk in functional optimization. So this is a different perspective on optimization compared to standard continuous optimization. So I don't know if it's going to be easier or harder to give that talk to an audience that maybe not as familiar with continuous optimization. So this is joint work with a quite large number of people. So Marlos is one of them. You had him talk last Wednesday, and then a bunch of others in RL and in optimization, both professors and students. Okay. Yeah, so this talk is a merge of 3 papers, 2 of them in reinforcement learning. So even though I don't do RL for the sake of RL, this is still a nice test bed in case of optimization. And as I said, this is quite a different perspective on optimization, so interrupt me at any time. Okay, so what does that mean, functional optimization, and how do we think functionally? So our goal is really to minimize some differentiable function h. Sorry, I'm assuming differentiability here. And this is a continuous space, of course. So theta, and I have d parameters, right? So I want to find a minimum of that function. And the standard approach of this, and if you read the textbook on continuous optimization, is you're going to do the optimization in theta space. So let's say you're going to do a gradient-based method. You're going to compute the derivative of the function h respect to theta, and you're going to go in the opposite direction of that derivative, right? And you can do all fancy stuff. You can do Newton method, everything, but they all rely on the derivative of h respect to theta, right? Okay. So this is the standard gradient step. Who knows about, quick show of hands, who knows about the equivalence between these 2 lines? Okay, 1 person. So this is the standard way we teach gradient descent, right? My parameter at time step t plus 1 is equal to my parameter at time step t minus some step size eta times the gradient of the function h at time step t, right? And you can show that this is a good thing because you can run the convergence analysis. You show that it converges nicely and you're happy. There's another perspective which is going to be very useful today, and I think in general this is useful, which is that of a surrogate. So what I'm going to say is my function h is going to be hard to minimize because potentially it can be complex. So what I'm going to do is I'm going to build a second order expansion of that function h around my current point. Right, so you can really view this as I'm building the second order Taylor expansion. So I'm building this quadratic approximation of my function h, and now I'm going to minimize this quadratic approximation instead of minimizing h. And if you compute the minimum of this quadratic approximation, you literally fall back on this, right? So you can really view gradient descent as I'm going to do the gradient and moving the opposite direction, or you can view, who knows about EM? Expectation maximization. Okay, so this is almost like some kind of EM. So I have my function. I'm going to build a quadratic approximation of it. I'm going to minimize this quadratic approximation. That's going to make me move. I'm going to make a new quadratic approximation, and I'm going to iterate like this, right? And so the quadratic approximation is really neat because then we know exactly how to solve it in 1 step, and we'll see more complex cases. But this quadratic approximation might be a terrible approximation of the original function h, right? So you in the spectrum in between simplicity and accuracy, we went all the way to simplicity, potentially at the expense of a lot of accuracy loss. We can replace the quadratic term here with some standard Bregman divergence that gives rise to mirror descent. Maybe Bregman divergence gives you a slightly better approximation. The issue with mirror descent is that we lose the analytic solution. So now we have to run an inner loop, outer loop algorithm. So we build that circuit, then we have to solve an optimization problem to minimize that circuit. When you reach a new point, we build a new circuit and we do it over and over again, right? And what do you need for this? So of course you want that minimize that surrogate gives you some guarantee on minimizing the original function. And one easy way to get this guarantee is that that surrogate is on an upper bound on the original function. And what you can do to guarantee that this is an upper bound, so the only free parameter you have at your disposal is the parameter eta. So eta needs to be small enough so that this is an upper bound, right? And you see that if your function h is smooth, then eta equals 1 over L is enough, and you recover the standard result in optimization. So instead of saying I'm going to do 1 over L because I have the convergence rates, I'm really going to take a perspective. Instead of minimizing the function h, I'm going to minimize a simpler function, and I want that simpler function to be an upper bound on my original function, so that I'm guaranteed that when I minimize that simpler function, I minimize I do improve my original function as well.
Okay. So like maybe this could be also a general question for all this, like optimizing the surrogate function, is it more expensive than the standard gradient descent, or like, it depends on the cases?
So if your surrogate function is quadratic, I know exactly the minimizer of this, and this is actually literally this, right? In the more general case, when this is, so in the general case, you can imagine even if h is non-convex, that surrogate function is a convex surrogate function. So it is generally easier. Okay. So I don't think parameters are very useful. And I think the reason why in optimization, at least in continuous optimization, we reason in terms of parameters is back in the day when we had linear models, and coming from statistics, the parameters kind of meant something. Right now we have deep nets, you have all of these symmetries, like it's impossible to reason in parameter space. We don't really know what the network does in parameter space, and really the only thing we care about is what kind of function it encodes. And again, in case of a linear model, you really have an equivalence between the parameters of your linear model and the function encoded by your linear model, because this is just a dot product. But within deep net, you give me a particular deep net with some parameters, I can find you another set of parameters that's going to encode the exact same function. So when you want to reason in terms of what do I want to do, what is a good function, reasoning in terms of parameters induces all of this added complexity that you really don't need to think about. The only thing you should care about is what does the function do? And pretty much this entire talk is about, can we think as much as possible, what does the function do? And I want to reason in terms of functions instead of in terms of parameters. So right now, this is all very abstract. So I'm going to tell you more about this. So usually, again, in standard machine learning, that function h that you want. Yep. Okay. So usually in machine learning, the function h that you want to minimize is the composition of two functions. So f is your network, is your model that takes parameter theta and then outputs the output for a particular data point. And then L is your loss, typically the quadratic loss or the cross entropy loss. So if I rewrite f of theta to be z, what I'm going to do is, instead of building my quadratic surrogate in theta, I'm going to build my quadratic surrogate in z. Right? And the reason is because if your function f is complex, this quadratic approximation to h is a terrible approximation. Your function is really non-quadratic in your parameters when you have a deep net because of all of these symmetries. But even if L is the cross entropy, the quadratic approximation of the cross entropy is a pretty good one. It's decent. Right? So does that make sense what I'm saying here? So when I said, you have the whole spectrum between accuracy and simplicity, and said when you build a quadratic approximation to theta, you go all the way to simplicity. Here, this is kind of a middle ground because I haven't told you yet how to optimize this, and that's not going to be as simple as a quadratic function of theta. But because this is quadratic in z, and so basically replaced L with a quadratic, this is a much more accurate surrogate of the original function I'm trying to minimize. Okay. Yeah, same thing. We can also use mirror descent, so replace that quadratic term with some standard pragmatic versions. Okay. So I'm gonna assume I have a finite data set, and Z is basically the concatenation of the output for all of the data points in my data sets. So if I have a data set of size n, and the output is of size k, this is an n by k matrix. And I'm going to on my training set. And we'll say, this is the matrix. And so I have the true output, which is basically all of the labels concatenated. I have the output of my function, and now the goal is really, I want to make the two as similar as possible. Right? That makes sense? Okay. Now, of course, there's one big issue, and the reason it's not that simple is that I cannot have any possible function output that I can think of, because I have some function class. And so there are some outputs I can have. If you have a linear model, then this matrix here has to be a linear transformation of my data matrix. But in general, the set of outputs I can get is defined by my function class, whether I use a big net or small net or something, right? So I can't have any Z I want here. So in fact, I actually have to solve a constraint minimization problem where I have to minimize the surrogates within the set of outputs that are in my function class. And that set in a deep net is incredibly nasty. It's not convex by any mean. I don't even know what shape it has. It's just a terrible set. I don't even know how to project on that set. Any questions so far? Okay. So what I'm going to do is when you want to optimize something over the simplex, there are two things you can do. You can either treat this as a constraint optimization problem, and you have to constrain to be part of a simplex, or you can parameterize your problem through a softmax, and then you guarantee to stay in a simplex. And you've kind of transformed your constraint optimization problem into an unconstrained optimization problem. So that's exactly what I'm going to do. Instead of minimizing a constraint optimization problem where my constraint set is really, really nasty, I'm going to take that surrogate and then replace Z here by f of theta. So instead of saying I can directly optimize over Z, but Z had to be part of my function class, is that Z has to be written of the form f of theta. So there are two Z's, one Z here and then one Z here. So there's one f of theta and then one f of theta. And so now I have a surrogate that's defined in terms of theta. But the difference between with the previous one is this one is not quadratic in theta, it's quadratic in f of theta. And what I gain is that this surrogate, again, is a much better approximation of the original function h than the one I had before. What I lose is that now I need to solve this over theta, which might not be as easy. And again, right now, you might be wondering why I do all of this, and that's going to become clear at some point. Okay. So yeah, so if my loss is convex, which honestly in 99% of the cases it is, but my function f is non-convex, which in machine learning now in 99% of the cases it's not convex. We basically doing optimizing over theta is basically doing non-convex optimization. Optimizing over f is doing convex optimization because L is convex, but then I cannot solve my projection operator exactly. So I'm doing inexact convex optimization. And it turns out that we had a paper 12 years ago now that tells you exactly how to do this. Okay, so what did we gain? And again, I'll go more into the detail, but so this is my surrogate function, and again, surrogate in f. And now I need to solve an inner loop, which is minimize this respect to theta. If I say I can't be bothered minimizing this inner loop exactly, I'm just going to do one step of this inner loop. So you take this and you compute the derivative with respect to theta, and you just do one step. What you end up with is exactly the gradient with respect to theta of your original loss. So just like I showed you, the equivalence is a standard update step is this minimization of this quadratic function. Now I can tell you the quadratic surrogate in theta is exactly like building this functional surrogate, but instead of minimizing the surrogate exactly, you just do one gradient step of that surrogate. The update you get is exactly the same. Okay. So gradient descent is equivalent to doing one gradient step in the inner loop. And so the question is there any case where we should do more than one gradient step? Okay. The biggest benefit is there are at least two main cases we identified, but there are probably others. Reinforcement learning and then bi-level optimization. Do people here do some bi-level optimization? Do people here do some RL? Okay, so the union is like 2.5 people. Okay, so the really great thing. So the problem in RL, and I guess, well, Marlos probably didn't really talk about this, but did you have so Marc Lanctot, I guess, maybe talked about RL. The main issue in RL is sample efficiency. The problem in RL is you have your policy that's parameterized by some network. Then to get the gradients of the function you're trying to optimize with respect to that the parameters of that policy, you need to collect samples in the environment. You collect the samples in the environment, you compute your gradients, you update your policy, and then you need to collect new samples under the new policy. And what people have been doing for the last 10 years is that, well, I can't be bothered. So I'm going to collect samples and then do multiple updates of the parameters of my policy, pretending that all is fine. But it's very, very hand-wavy. And what we show here is that this is actually a natural thing to do, and you get convergence guarantees when you do this, when you do it properly, and PPO doesn't do it properly. So why is this? Because this surrogate, and I ignore the constant term, right? So this is the surrogate we want to optimize. There's one thing that you need to look for, is that in RL, collecting samples for the environment is because you want to know, does my policy perform well in the environment? So going back to this, in RL, F is your policy. So theta are the parameters of your network, and F of theta is your policy. Basically, F of theta is a set of conditional distributions of actions given states. And then L is the environment that tells you, if you use that policy in that environment, are you going to do well or not? And so the cool thing about this is that computing this gradient requires interacting with the environment. So it requires collecting samples because it involves L. But then everything else does not involve collecting samples. So think of it this way, and to me, that's the best way to present this. Standard RL, you collect samples, and I tell you what is a better set of parameters. And you update your parameters, usually not that much. And now you need to collect samples to know again what's the best set of parameters. In a functional approach, what it tells you is you collect samples, and that tells you what is a better policy. How should your set of conditional distributions change so that you perform better? I'm not talking to you about the parameters. I'm just saying to you, this would be a better policy. And now you can do as many gradient steps of the parameters to try to be as close to that policy as possible. But you don't need to interact with the environment anymore. Interacting with the environment was only there to tell you what a better policy would be. And internally, you can almost view it as like an API. And then internally, you can do whatever you want to get closer to that policy. And these are really two different things. And given that new policy, again, you don't need to interact with the environment anymore because you already know what the better policy would be. And so now you can afford to do many, many gradients updates to your network to match that policy.
And the policy you get it from the analytical
analysis.
From
yeah, so
but the best policy you get it from analytical.
So yes, so imagine that I ignore the fact that Z cannot be anything. I'm pretending the Z can be anything. I know exactly what Z minimizes this. This is minimizing the quadratic. And so Z is almost going back to the original point. I have ZT plus 1 equals ZT minus eta times the gradient with respect to Z of my loss. That's my dreams better policy. Yeah. And now I have this policy that I know. I have the actual policy with the current set of parameters, and then I can minimize the divergence. Not any divergence, I need to be careful, but basically minimize the divergence between the two policy. And whenever I'm bored, I stop, and then I collect new samples. Right?
To be clear, in the reinforcement learning problem, you are thinking of it as a bi-level problem. Is it like that? That you have your policy, but you don't know how it will perform in the actual environment, and then you are taking gradients with respect to the policy to improve the policy, and then you are testing it in the environment itself. Is it like that? Or?
So this loss here, this surrogate tells me exactly, you can give me any policy Z, and I can tell you not how it would perform, but I can tell you the approximation. Yes. So I can tell you a lower bound on the performance of that policy.
Yes.
So now you don't need to query the environment anymore. Given any policy, you have the lower bound on how that new policy would perform. Okay, and now you can take this with you. You don't need access to the environment anymore, and you can test any policy you want against that loss.
Okay, nice.
Right? So, when you it's trivial. I mean, it's basically I just replaced the true reward with a Taylor expansion. I just did a Taylor expansion in policy space instead of doing it in the parameter space. And bi-level optimization, exactly the same thing. For those of you, I don't know if you've done distillation. Distillation, there's a teacher network and a student network. Same thing. The teacher network, it doesn't give you a gradient of the parameters. The teacher network tells you, here's what your student network should do. Once you notice, you can do as many of these as you want. So you can query the teacher network once to get what the student network should do, and then you can do as many of these as you want. And so depending on the relative cost of querying the teacher network, it might be useful to do this only once in a while. And in RL, it's clearly the case. And again, people do this. Okay. Okay, so there's this. Yeah, there's a whole bunch of results. I think so. I don't know. Do I mention this? Yeah. So okay, this is an imitation learning experiment. So you have an agent that we're trying to mimic, and what we compare. So you have AdaGrad, Adam, SLS is stochastic line search. These are all the first three are all well, actually the first four are all in theta space. And actually, so okay, the first three are in theta space. The last four are in function space. And the term here is how many gradient steps of the inner loop do we do before recollecting a gradient. And so SSO1, because we only do one gradient step, that's going to gradient design. And on the x-axis, you have number of interactions with the environment. And so obviously, if you do more steps in the inner loop, then you need to have far fewer interactions with the environment to reach the same level of performance. There's something else. I don't know if it's in this talk, so I'm going to talk about it now, and maybe we're going to see it later. There's something that really bothers me in reinforcement learning. So maybe that's one of the reasons why I don't do that much RL anymore. Is you have a lot of results in a tabular setting. So tabular setting means I can basically, when I said your policy is the set of conditional distributions of actions given states, tabular setting means you don't have that many states, you don't have that many actions, and you directly optimize over that matrix of conditional distributions of actions given states. And to me, this is a very unrealistic environment because in general, you have far more actions and far more states. So really, you have the theoreticians of RL that like to prove stuff in the tabular setting, and you have the practitioners that said that's of no use to me. I use function approximation. But if you go back to this is your tabular representation. Z is your policy. It said Z is literally the matrix of the conditional distributions of actions given state. So the tabular setting is basically saying, oh, I'm in the case of where theta equals Z, and then f of theta is the identity matrix. But I can naturally extend the results in the tabular setting to any function approximation setting. The only difference is in the tabular setting, I can solve this exactly because instead of being, because it's quadratic in Z, it's also quadratic in theta. And in a function approximation case, I cannot solve this exactly. So now the only thing that matters is not whether or not I'm in a tabular setting or not, it's how well can I minimize this function. And again, if we go back to that paper, it actually gives you a convergence rate depending on how well you can minimize that function. So the only thing specific about tabular is that you can minimize this exactly. But if you have linear function approximation, for instance, you can also minimize this exactly. This is also convex. So in our last paper, we actually extended a whole bunch of results from the tabular setting to the more general setting. Okay. So yeah, actually. Yeah, so RL, so standard reinforce, it's basically this, where you do one gradient step and then you reinteract with the environment. So no one uses reinforcement anymore. This is just way too expensive. And again, TRPO, PPO, MPO, which are I think it's trust region policy optimization, proximal policy optimization, and M policy optimization. Forgot what the M stands for. And these ones don't have any theoretical guarantees. Well, they only have them in the tabular set. And you can see actually these methods do fail in practice if you're not careful about the hyperparameters. And so what we have, I actually don't want to go through the details. I don't think it's that interesting. It was way too mathy, but it's basically there's one thing that I want to say. Where is it? You want to say this? It's full burden of very good stuff. Yeah, okay. So still, I want to explain to you the algorithm. So we have a functional representation of a policy. And here, okay, I'm going to say more, but because so far I haven't said anything. I said this is a conditional distribution of actions in given states. This is slightly more generic. And so what we're going to have is an inner loop, outer loop algorithm, as I described. So first, you compute the gradient, and for this, you need to interact with the environments. And that allows you to formulate the surrogate. And then, given that surrogate, then you can do as many gradient steps as you want. And again, these do not require interacting with the environment anymore. And then once you're happy, you get your new policy, and then you start again. The funny thing with this method is that, going back, this functional representation, you actually, for policy, you have different ways of representing a policy. It can be the conditional distribution of actions given states. It can be the logits of the conditional distribution of actions given states. Or you can even imagine is the discounted state visitation distribution. They all give rise to different algorithms. And some of them work better, some of them work worse. But basically, you can recover all of these existing algorithms based on two things. And we show again that PPO, MPO, they do the wrong thing, but you can do the right thing. They depend on two things. They depend on what do you use. I'm sorry, go back to this. What do you use as functional representation? And then if you use mirror descent, what is the divergence you use? You have the two free choices for these. Based on these, you can recover a whole bunch of RL algorithms. And so, for instance, the reason why PPO fails is that they use something that's not a Bregman divergence. For those of you who know, there's a forward KL divergence and a backward KL divergence. The correct one to use for them would be the backward KL. It's like, we can't be bothered. That's too complicated to optimize. So we're going to use the forward KL, which can lead to divergence. And you can show that's because they use so if you use a different functional representation, so a different set of Z, then you can get the forward KL as a standard Bregman divergence. And then we showed that this is much more stable and you can do a whole bunch more stuff.
So when you say it's wrong, in what sense do you say it's wrong?
So there's this weird thing about Bregman divergences. Okay, so Z, this is a bit technical and weird, but this is also fun. So okay, Z can either be a probability, the functional representation I can represent the probability, or it can be the logits of the probabilities. Does that make sense? The difference between the two? Okay. So imagine here that there's a Bregman divergence. For the probability, if you use Z for them to be the probabilities themselves, the only KL that's a Bregman divergence is the reverse KL. So there's no mirror descent algorithm with the forward KL when Z is the probabilities themselves. If Z are the logits, the only KL that's a Bregman divergence for the logits is the forward KL. And how does that differ? Well, here I take the derivative of my loss with respect to Z. So either you take the derivative of the loss with respect to the probabilities themselves, because as you said, Z are the probabilities, then you need to use the reverse KL. Or you take the derivative of the loss with respect to the logits, and then you can take the forward KL. It's you can do both, but you cannot mix and match. And they do mix and match. And so what we did is we agree that the forward KL is nice. And so instead of doing SPPO, taking the derivative with respect to the probabilities, we take the derivative with respect to the logits. And so it gives a slightly different method that has very nice convergence properties. So it's a one-line change. And this is an open question, like when is working with probabilities better than working with logits? We don't have the answer to this. And it'd be interesting to know, but in practice, we just try both and then we see which one goes best. Okay. Yeah, I tend to, these slides are from one of my co-authors just right now, and I tend to feel less about the technical math and more about the intuition. So can I just move this? Yeah, I'm sorry, this was a rhetorical question. Yes, so I said, I'm going to go back to, instead of getting the true loss, I'm going to build that surrogate. And so how can I guarantee that maximizing that surrogate actually does something meaningful for the true loss? Well, I need two conditions. I need to, my surrogate needs to be tight at the current point. The two values need to be the same. And I basically, again, for those of you who know EM, I'm basically repeating what EM does. So my surrogate needs to be equal to my true function at the current point. I need to be able to maximize my surrogate. And this needs to be a global lower bound. If I have all of these conditions, I'm guaranteed, right? So there's the simple drawing. If this is, I'm putting the, yeah. So I want to maximize this. No. I can do multi-card. Usually the black one's the one. Okay, good. So this is the function I want to maximize. And this is my current point, right? So if I can build something like this, that's a lower bound, and that's tight at the current point, I'm guaranteed that if I improve this one, I'm also going to improve my function. And so here, let's assume I improve it exactly. I write here, and then I'm going to build another.
So this is the opposite case of learning very well to minimize functions. So
Oh, it's just
the
that
upper bound.
Yeah, it's just that RL tries to tend to maximize the reward, and deep learning wants to minimize the loss. But I can exactly do the opposite and then replace that lower bound with another. Okay. Yeah, the only issue is that this talk works for both supervised learning and RL, and sometimes we talk about gradient descent, sometimes talk about gradient descent. But that's the idea. Okay, so if your conditions are satisfied, and so the great thing, when I told you, we can lift all of the results from the tabular setting, if we have all of these conditions, then we do have convergence to a stationary point, and I haven't said anything about the policy parameterization. The only price I will pay for a policy parameterization that's complicated, like a deep net, is that I'm not going to maximize that loop very well. So maybe it's going to take me more steps, or I need to build a circuit. But I'm still guaranteed to improve. So no matter what policy parameterization I have, I am guaranteed to reach a stationary point of the original function. Which, as far as we know, in RL, people only had guarantees for the tabular setting, and it had no guarantees whatsoever for the general function approximation setting. Right? So we basically recovered what standard supervised learning has known for like 60 years at this point. But for some reason, RL has been lagging behind.
Here, there is no result about the construction of this loss function, right? It has no, how do you construct it to be tighter approximation?
No, so, okay, that's a very good question. So no, any surrogate that satisfies these conditions is fine. And so this surrogate, is basically the constant term to ensure that it's the same value at the current point, a linear term. And then you have that term. And this is basically so the two choices you have here are the choice of function phi and the choice of step size eta. And yes, right now it's basically choose the phi so that the circuit is as good as possible. In practice, honestly, again, when people do mirror descent, they use the phi, like the negative entropy or the log sum x. They basically use the phi that leads to the KL. But there might be fancier ones. I don't know. In fact, you can still have a phi for different states in RL. So yes, there's an open question about how do you design a good phi so that this is true. A much simpler question is, given a phi, how do you set the eta so that these conditions are guaranteed, right? And again, there's another neat thing about this is that in the quadratic case, eta here depends on the loss respect to theta. So it's the smoothness respect to theta, which is usually extremely hard to assess. Here, that's the smoothness respect to pi, to the policy. And again, that's usually a whole lot easier to assess because I've ignored all the complexity of how pi depends on theta. It's just how does my environment depend on the policy? So this, and we can show, for instance, in RL, eta is basically 1 over 1 minus gamma. Again, regardless of the parameterization of how you parameterize your policy. Okay. Any more questions? Yes.
When do you stop?
Yes, good question. When do we stop the inner loop optimization? We don't know. When we're bored. That's why this plot earlier has 1, 10, 100, and 1,000. There's the hand waviness that if collecting samples is very, very expensive, then clearly you want to do more inner loop steps. We'd like to have some guarantee. I think it's so right now what we have is even worse than this, which is no matter how many steps we do, because we're solving the inner loop, we're guaranteed that we're going to optimize the original function. We have nothing that tells us that doing more than one step is beneficial. In practice, it is, but it could be very well, like you could imagine, right? That my lower bound, for some reason, is how do I put it? Okay, let's do it this way. It's probably not true, but let's do it this way, like this. And so if you only optimize your lower bound a little bit, you're going to arrive here for the original function. But if you optimize it a lot, you're going to arrive here. That's much, much worse. So, I mean, that's the price we pay for not interacting with the environment during the inner loop, is that maybe in some cases the surrogate is good, maybe in some cases the surrogate is bad. Yeah, we don't know. That's why our current results are pretty weak in that sense. Like we can only guarantee convergence to a stationary point, but in terms of rates, we don't do it. We cannot prove any better rate than just doing one gradient step.
But maybe that is good because it gives you like a fast look at approximation, if I understand correctly.
Yeah, but I mean, we'd like to be able to give some guidelines about how many inner loop steps do you need to do, and we don't. Okay. No, okay, so this is actually really cool. This is written in a terrible way, but this is really cool. So this is a paper that we just submitted to NERPS, and it's much more general than the way we present it. And I wish we had we do have the simple equation. I love it. So the problem with our framework is when we build the surrogate, we assume we have access to the true gradients of the loss respect of the function. And in practice, you don't have access to the true gradient. You either have access to a stochastic estimate of the true gradient, but in the case of RL, sometimes people use a critic, so we only have access to a model of the true gradient. So here you have your linear term, and normally my linear term includes the true gradients of the loss respect to pi. But in many cases in RL, you replace this with some approximate gradient G hat. Again, without going to the detail, that's a critic, but basically that true gradient, we can have an unbiased estimate of that true gradient, but super high variance. And so we usually replace this with a much lower variance, but biased estimate of the gradient. And the question is, how many guarantees do you lose when you replace the true gradient with an approximate gradient, as everyone uses in practice? And so this is your linear term. This is your standard divergence term. And the price you pay for using G hat instead of true gradient is this additional term. And you see in the middle of that additional term, you have the difference between the true gradient of J respect to pi and G hat. So what this tells you is when you're optimizing the surrogates, you're relying on me to give you the true gradient. Now what I'm telling you is I can even give you the wrong gradient and you can still optimize the surrogate. And the price you're going to pay is this blue term. And so now when people do actor critic, that's something that's been bothering me for so long. Maybe you probably have the same thing in discrete optimization. People build a complex system with the interaction of many modules, and they have a global objective. And they're not able to decompose, like to translate the optimization of the global objective into a optimization of each module independently. So in RL, they have the actor, which is how the agent works in the world, and the actor is used by a critic. And the way they turn the critic is not related to how it's going to be used by the actor. So they don't have this single objective, which is I want my actor to perform well, and I'm going to use the critic so that my actor performs well. They say, my critic, nah, I should kind of estimate the Q value, so I'm going to design a loss for this. But they have absolutely no guarantee that if the critic does a better job, the actor that's going to use the critic is actually also going to do a better job. Does that make sense? And so as you build more and more elaborate systems, which all of these interdependent parts, it's really, really important that the loss for each of these individual parts relates to the main loss that you're interested in. And standard actor critic doesn't do this. But now that you have this loss, the goal here is the price you pay for using a model of the gradient that's not equal to the true gradient. So now we exactly have a loss for the critic. The goal for the critic is to minimize that blue term. Because if you can minimize that blue term and make it 0, then you go back to the case where you have the exact gradient. Okay. So this is, again, as far as we know, this is the first case in actor critic in RL. And actor critic has been, I think the first paper is like 2001, where we have a single joint objective over the actor and the critic. So going back to this, I think this is really cute. What we had before, remember, you had the lower bound was tight at the current point. When you use the wrong gradient, your lower bound is not tight, and the looseness of that lower bound is exactly the blue term. So what does that mean for you? Is if you use a wrong model of the gradient, because that lower bound is loose, right? So loose lower bound means this. Color. So this is my current point. Instead of being tight, now I'm going to be slightly lower. I'm going to be like this, right? And now, because I'm minimizing a lower bound that's loose, it's very possible that I'm going to improve the lower bound, but I'm going to decrease the objective. I lose the improvement guarantee, right? If you want to maximize this and the lower bound is there, because it's terrible, usually you can do whatever you want here if there's no relationship with it. So the price you pay for having the wrong gradient is you lose this monotonic improvement guarantee. And the bigger the blue term is, so the more wrong your model is, the more you lose that improvement guarantee. And what we can show is that there's still a way to recover that improvement guarantee as long as your error is not too big.
So that's basically the reason why you don't know when you have to stop.
No, because this is the error when our convergence result that we converge to a stationary point is independent on how well we maximize the lower bound. This is how good our lower bound is, not how well do we maximize it. I'm giving you a lower bound. If I'm giving you a tight lower bound, you can do whatever you want. You're going to reach a stationary point and you're going to be happy. Now, if I give you a bad lower bound, you can potentially get terrible results.
Okay.
And so the worst quality of the lower bound I can give you so that you can still have improvement guarantee is defined by this. So this is my estimate of the gradient. This is the true gradient. So basically the norm of my estimate needs to be bigger than, well, let's say the difference between the true gradient and the estimate. The square norm needs to be lower than the norm of the estimate. If I have this, you can still recover your improvement guarantee. If I'm above, because your model of the gradient is really, really bad, then you know at this point, like you shouldn't even try to optimize the lower bound because you have no idea what's going to happen. And again, this is a result that we don't think exists before. And the way people handle this when they do actor critic is they make a huge network for the critic to try to have as little an error as possible, because as soon as they have an error, they lose all convergence guarantees. Was what we say is, no, you can still have an error as long as it's not too big. Okay. Yeah, so this is basically, as I said, for any critic error, if it's not too big, then we converge to a neighborhood of stationary point. So this is what it looks like in practice. This is ugly. Let's not go into this. So this is so we compare standard actor critic to our method, and for different capacity of the critic. So this is a big critic with 80 parameters. This is 60 parameters, and this is only 40 parameters. And so when your critic is really powerful, it's really good approximation of the gradients. No matter what you do, you're fine. And so all of these methods converge to the optimal policy. As soon as your critic starts to become bad, then standard actor critic, these are the blue curves, just the performance drops. You lose all guarantee. But if you do it properly, like in red, then you get you actually get convergence to the optimal policy, even if you had an error in the curve. Right? So I actually, sometimes I try to summarize the research I've done over the last 20 years. And then Feng mentioned the stochastic variance reduced gradients. In machine learning, and again, I'd be happy to know whether this is the same in discrete optimization. You usually have tons of information to which you have access, but that's not exactly the one we want. Like I have these gradients, but maybe they'd be slightly old. Like they were computed on a slightly different set of parameters. And the whole field of machine learning basically relies on throwing away this information and only using unbiased estimates. For instance, something that bothers the hell out of me, and that's something I'm working on right now, is you want to solve a problem. You have these hundreds of models available on the web that have been trained on different problems, but we don't know how to use them. So you want to solve your problem, you're going to train from scratch. And like this huge amount of compute has been done. And the only reason is they might be useful, but maybe not all of it, maybe a subpart of these models. Which model do we choose to start from? And so we're going to try a bunch of them and then see which one works best. But this is extremely manual. And our paper that got us a Lagrange prize was exactly showing that in the case of optimization, you can use the old gradients in a way that still gives you convergence guarantees. And to me, this is a direct continuation, which is your model of the gradients might be wrong. It's fine. You can still converge as long as it's not too wrong. And so again, I don't know how it is in discrete optimization. I think in terms of machine learning in general, we need to have more theoretical guarantees about what happens when we use estimates that are not exactly the ones we want, but they still might be related. Okay. So yeah, casting optimization, as projected functional optimization. Honestly, what appeals to me is the perspective. I think it's much cleaner to view this as I'm going to optimize the function and I'm going to try to find the parameters to match this, rather than I'm going to do the optimization in parameter space. It also turns out that in some cases, it leads to more efficient methods, especially in cases, as we discussed, reinforcement learning, bi-level optimization, where getting the gradient of the loss is expensive. And so you really only want to do this once for multiple gradient methods. And it gives you convergence guarantees in a much wider range of settings. What more can we do? So this is what I've been wanting to do for the last 2 months. I need to find the time to code. Who knows about Nesterov acceleration or momentum? Virtual hands? Don't be shy. Okay, more. I think that's the best show of hands I've had since the beginning. So you have standard gradient descent, and then there's a method for strongly convex function that's called Nesterov acceleration that converges faster than standard gradients. And this weird thing, and you have, I don't know how many tens of papers trying to explain why this works. I still don't have a good understanding of why this works. I just know it does. So you do your gradient step here, and I've kind of changed the notation. So the standard gradient step would be yt plus 1 equals yt minus the gradient constant. How's the knee? But here, what you do is you take this update that would be your gradient updates, you put it in WT, and then you do some extrapolation step. That is, you would go, this is super weird. So, and honestly, the proofs show that works, but I feel it doesn't give you any information. So your okay. So you are, there's YT here. And then basically you're gonna go here. That's gonna give you WT plus 1. But then the old WT was maybe earlier. So overall, basically, let's say you move in this direction. And what that tells you is that, oh, I moved here, I'm going to continue moving here. And that's a terrible little drawing, so I'm going to do another one. So you have one that's clear. So I'm going to minimize a quadratic function. So these are the level sets of the quadratic. And so it's much more curved in one direction than in the other. And what's going to happen if I do gradient descent on this is it's basically going to do this. This is gradient descent. Okay. Right. And the problem with gradient descent, if you're familiar with optimization, is because this is very curved in this direction, I can't use too big a step size because otherwise I'm going to diverge in this direction. So I need to use a small step size to not diverge in here, but because here the curvature is very small, I'm going to be extremely slow in this direction. And so the price I pay in gradient descent and the speed of gradient descent is determined by the ratio between the curvature in this direction and the curvature in this direction. And if the ratio is extremely high, gradient descent is extremely slow. So what Nesterov does is it first does the first gradient step the same. Does any of you see the line? Why? Okay. So what Nesterov does is the first gradient step is the same. And then the second one, instead of going here, it says because I moved in this direction for the first step, I'm going to continue moving in this direction a little bit. So I'm going to dampen my updates. And so I'm going to do a mix of this and that. And so maybe it's going to be this. And so overall, it does something like this, and it converges much faster. In Nesterov, we know it works like for strongly convex function, we have the guarantee and we know that it works much faster. For general non-convex function, we have no idea what Nesterov is. So I'm assuming all of you know Adam, which is the standard optimizer for optimization now for deep nets. Adam implements some kind of Nesterov acceleration, but they do it in parameter space. And honestly, it works. It's not clear why it works. The proof in the original paper is wrong, but it does work well. But it has no reason to work in a very complex space like the one of the deep nets. But the space of the function is strongly convex and is very well behaved. So what happens if we do Nesterov in the function space? So now, when I told you, you build a surrogate and that tells you what your policy or what your function should be, and then you're going to try to match that function with your parameters, you're going to do Nesterov. So you're going to do this exact same trick, and that's going to tell you what your function should be. And it's not just after functional gradient step, it's after something slightly fancier. But then from your perspective, I gave you, said, this is your target. This is the function you need to achieve. Find me the parameters that achieve this. And then you solve the exact same problem on the, right? So this is my old, okay. So, and what you can show, I don't want to go through the details of this. What you can show is that if your function is a linear function, so the output of my function is my design matrix times W, then whether I do acceleration in a function space or acceleration in a parameter space is exactly the same thing. So my claim is that people have been doing Nesterov in the parameter space, but from the get-go, they should have done it in the function space, but they didn't realize they were wrong because for simple models, these are equivalent. But as soon as we move to more complex models, these two become distinct, and we actually need to do it in function space. Okay, so yeah, anyway, it tells you how to do it. I just need to find the time to implement it. But you can view it I think extrapolation in function space kind of makes sense, right? Which is, have you had a talk by Damien Sieur in the last 2 years? No? Okay. He's in Montreal. He's really excellent. And it's basically the idea that when you see multiple points along your optimization, you kind of you're able to figure out the dynamics of the optimization and kind of predict where your optimization is going to end up. And so this is exactly the same. You see my function at the current step, you see my function next step, and you kind of see the trajectory. And so you can extrapolate in the function space and say, well, given that I had this function, then that function, then that function, then this one's probably a good. So you extrapolate in function space because that trajectory is fairly easy. Okay. Yeah, other questions. So yeah, should we study optimization trajectories in function space? There's a bunch of papers in machine learning. What does the optimization look like? And they look from the parameter space. Like, do my parameters live in a low dimensional subspace? I think it's fine. But if you have two models of different nature with different sets of parameters, you have no way of comparing what they do. Whereas if you compare in function space, because they have the same output, then suddenly you can compare these trajectories in function space. We talked about games. You said you had a class on games. Oh no, some people here do games. Okay. So at MILA, there's a bunch of people who do games. These are mostly bilinear games. Okay, that's fine. But now, if you treat this, if you say this is a bilinear game, so you have two players, X and Y, but X is actually a function of some theta, and then Y is some function of some other theta. So it's still bilinear in the outputs, but then you can have much more complex functions that represent these two players. So then you can probably study the dynamics of these games, which are bilinear in function space, but not bilinear in parameter space. Was at least again at MILA, the people I know who will do this do work in the bilinear case in the parameter space. And then one last thing, performative prediction. Who knows what performative prediction is? Okay. It's the idea, it's usually when you deploy a system in the real world and the users of the system are going to adapt what they do in response to that system. So if you have, a university acceptance system, then students are going to study different things given the acceptance system. And so there's a dynamic going on between you want your system to work well for the current distribution of students, but then students change their distribution in response to this, and so you can study the dynamics. And so you want to find the parameters of the system. So when you change theta, which are basically your university acceptance system, the acceptance changes, but then the distribution of our students changes as well. And so you need to study the dynamics of this, which is a bit nasty because you have these two terms that depend on theta. And basically what we show is that you can upper bound this that you want to minimize with two terms where you had P and you had L, and this one only depends on P, and this one only depends on L. So there's this more general idea, and there's another paper I haven't talked about that we're working on probably for ICARE, where it's basically when you have this complex systems with many modules, there are ways to break them down through upper bounds and find an upper bound on all of these modules, but then all of these modules are now optimized independently. So it goes back to what I was saying earlier, which is how do you decompose a single global objective that depends on many components into a bunch of individual objectives, such that when you minimize these individual objectives, you still have a guarantee on the global objective that you had at first. And again, right now in machine learning, this is very heuristic. And we usually lose all guarantees when we try to optimize these components individually. Okay, that's it. So yeah, this was based on 3 papers. We probably have a couple more coming out in the next few months. I'm happy to take any question right now, or otherwise you can just reach out to me. This direction, I'm hiring master students, PhD students, postdocs on it. So if that's something that interests you, reach out to me as well. Thanks.